In this lecture, we talked about the Bayesian classifiers. The Bayesian classifier is a probabilistic framework for solving classification problems. The conditional probability of class C given attributes A is equal to the joint probability of A and C divided by the probability of A. And also the probability of the attributes A given the class C is equal to the joint probability of A and C divided by the probability of C. The Bayes theorem says that the probability of class C given the attributes A is equal to the probability of attributes A given the class C times the prior probability of C divided by the probability of A. Given a data set, we consider each attribute and class label as random variables. Given a record with attributes A1, A2, and up to AN, the goal is to predict class C. And specifically, we will find the value of C that give the maximal probability P of C given the attributes. The posterior probability P of C given the attributes is equal to probability of attributes given the class times the prior probability of C divided by the probability of attributes. Choosing the value of C that maximizes the posterior probability is equivalent to choosing the value of C that maximizes just the numerator of the right hand side. The question is how to estimate the probability of attributes given the class. Assume independence among attributes AI when class is given. Then we can write probability of attribute A1, A2, etc. up to AN given the class C, and C is equal to Cj is equal to the product of the probabilities of attributes AI given Cj, where I is equal to 1, 2, etc. up to N. We can estimate probability of the attribute AI given the class Cj for all AI and Cj. And a new point is classified to the class Cj if the numerator in the right hand side is maximal. This slide shows an example how to estimate probabilities from data. Looking at the class information, you can see that the probability of no is equal to 7 divided by 10. There are 7 records with no, and the total is 10. And similarly, the probability of yes is equal to 3 divided by 10 because there are 3 records with yes, and the total is 10. For discrete attributes, we can compute the probability of the attribute AI given the class CK by the number of instances having the attribute AI belongs to class CK and divided by the total number of instances that belong to class CK. For example, the probability of status equal to merit given the class is no is equal to 4 divided by 7. That is because amongst 7 records of no in the class information, there are 4 records with the status equal to merit. And similarly, the probability of refund is equal to yes, given the class is yes, is equal to 0. That is because in the data set, looking at records with yes in the class information, we see the attribute refund has all no value. For continuous attributes, we have several ways. We can discretize each continuous attribute into bins, or you can do two-way split, or you can assume a certain form of probability distribution for the continuous variable and estimate the parameters of the distribution using a training data. This page shows an example of estimating the parameters of the distribution and use those to calculate the probability of income equal to 120k given the class equal to no. This page shows an example how to classify a test record. X with refund equal to no, and status is merit, and income is 120k. From the data set, you have computed that the probability of attributes given the class either no or yes. Taxable income is a continuous attribute. For class no, you compute the sample mean and the sample variance. And for class is yes, then you also compute the sample mean and the sample variance. And from there, you compare the probability of the test record X given the class no times the probability of class no, and also probability of the test record given the class equal to yes times the probability of class equal to yes. The left side is actually greater than the right side, so the conditional probability of class equal to no given the data is greater than the probability of class equal to yes given the data. So from here you can say you classify the test record to no. If one of the conditional probability is 0, then the entire expression becomes 0. So you can either adjust the probability of the attributes given the class using Laplace or M estimate. The Naïve-based classifier is robust to isolated noise points. It handles missing values by ignoring the instance during the probability estimate calculations. Robust to irrelevant attributes. Independence assumption may not hold for some attributes, and here we can use other techniques like Bayesian belief networks.